Assalamualaikum and good day to all of you. In all our previous lessons, our focus was mainly on ordinary differential equations, ODEs, and their methods of solutions. But today we are going to switch our focus to partial differential equations, PDEs, and we are also going to learn a basic technique of solving PDEs by using the method of separation of variables, hence the topic separable partial differential equations. Hopefully, by giving you a brief exposure to this topic, you will have a feel of what PDEs are all about. And if you want to learn more about other techniques of solving PDEs, you can take numerical methods or other classes that focus on PDEs. As in ordinary differential equation, a partial differential equation may also be linear or nonlinear. Let us now look at the general form of a linear second-order partial differential equation, which is given by equation number 1. A del 2u del x squared plus b del 2u del x del y plus c del 2u del y squared plus d del u del x plus e del u del y plus fu equals to g. Take note that u is the dependent variable and x and y are the independent variables. So since this equation contains more than one independent variable, therefore we identify equation number 1 as a partial differential equation. And take note that the highest derivative that appears in this equation is 2, and therefore we call this as a second order PDE. This equation is also said to be linear. Now how is that so? Take note that this equation fulfills the characteristic of a linear equation because u and all its derivatives are all to the power of 1. Besides, the coefficients a, b, c, d, e, and f, as well as the function g on the right side, they are all functions of x and y. In other words, they are functions which do not contain the dependent variable u. Okay, because of that, we identify this equation as a linear partial differential equation. The equation number 1, as shown in the previous slide, can be considered as homogeneous or non-homogeneous depending on the function g. Okay, let me show you again equation number 1. So this is equation number 1. Okay, so if g of xy is equal to 0, then the PDE is said to be homogeneous. But if the g of xy is not 0, then the PDE is said to be non-homogeneous. Example, okay, so here's a second order linear PDE. I notice that the g of xy is equal to 0, so we consider this equation as a second order homogeneous linear PDE. In the next example, the g of xy is not 0, and therefore we describe this equation as a second order non-homogeneous linear PDE. Now we are going to learn how to classify a second order linear PDE. Let us refer to equation number 1 again, but this time A, B, C, D, E, F, and G, they are all real constants. And for this equation to remain as a second order PDE, A, B, and C cannot all be 0. In other words, at least one of these three, A, B, and C, is not 0. Define the discriminant as b squared minus 4ac. Now remember, a, b, c, they are all constants. Suppose we are given a PDE and we calculate the value of the discriminant b squared minus 4ac, and we find out that the value is less than 0. If the value of the discriminant is negative or less than 0, then we conclude that the equation is classified as an elliptic equation. Let's look at this example. Del 2u del x squared plus del 2u del y squared equals to 0. Now what type of equation is this? Is this an elliptic equation? Compare this equation with the general equation shown in equation number 1. Now a is the coefficient for del 2u del x squared. In this case, a is equals to 1. B is the coefficient for this mixed derivative. but there is no mixed derivative in this given PDE, therefore B is equal to 0. C is the coefficient for del 2u del y squared. C in this given PDE is equals to 1. Okay, now substitute A, B, and C into the formula of the discriminant, and you find out that the result is equal to -4, a value which is less than 0. And since the discriminant is less than 0, we conclude that this given PDE is classified as an elliptic equation. Now this given PDE has a special name given to it. It is known as a Laplace equation. A Laplace equation describes a 2D steady-state temperature distribution where U is the dependent variable, U is the temperature that depends on the spatial variables x and y, and the temperature U is independent of time. The Laplace equation is also applied in electrostatic and fluid flow. If b squared minus 4ac is exactly equal to 0, then the given equation is classified as parabolic. Let's look at this example. Del 2u del x squared equals to del u del t. In this equation, u is the dependent variable, x and t are the independent variables, and t is replacing the variable y in the general equation. Now, what type of equation is this? We are going to know its type by calculating the discriminant b squared minus 4ac. And to do that, we are going to firstly shift del u del t to the left side of this equation, and we get this form of expression. And from here, we can identify the values of the a, b, and c. Now, a is equals to 1, the coefficient of del 2u del x squared. B is the coefficient of the mixed derivative. In this given PDE, there is no mixed derivative, and therefore B is equal to 0. C is the coefficient for the second derivative of u with respect to t, and that means C in this PDE is equal to 0. Now this term here is comparable to the term shown in this general equation, and therefore we say E has to be equal to -1. Now, however, E is not used in the calculation of the discriminant. So let us calculate b squared minus 4ac based on the values a, b, c that we have got. And it seems that b squared minus 4ac is exactly equals to 0. And therefore, we conclude that this PDE is a parabolic equation. Now, this PDE is known as a one-dimensional heat equation that describes temperature distribution over time along a heated rod. Okay, now U is temperature, and U is dependent on the time t and also the spatial variable x. If b squared minus 4ac is larger than 0, then the given equation is classified as hyperbolic. Example, del 2u del x squared equals to del 2u del t squared. Okay, let us identify the type of this equation by calculating this discriminant. So firstly, we are going to shift del 2u del t squared to the left side as follows. Okay, from this equation, we can know the values of the a, b, and c. Now, a is the coefficient of del 2u del x squared. Certainly, a is equals to 1. B is the coefficient of the mixed derivative. Now, there is no mixed derivative in this equation, therefore b is equal to 0. Now, this term here is comparable to the term in the general equation, and therefore c is identified to be equals to be -1. Calculate the discriminant b squared minus 4ac, and it is found that the value is equals to 4, a number which is larger than 0. And therefore, we conclude that this given PDE is a hyperbolic equation. Now, this given PDE is known as a wave equation that models the vibration of a string in one dimension, okay, where U is dependent on the time and also the spatial variable x. Let us now answer some questions. Classify whether the following PDE is elliptic, parabolic, or hyperbolic. The first question is del 2u del x squared minus 3 del 2u del x del y equals to del 2u del y squared. To find out the type of this equation, we are going to firstly shift del 2u del y squared to the left side. and compare this equation with the general equation given in equation number 1. Okay, so by comparison, we consider A as equals to 1, B is equals to negative 3. Okay, this negative 3 is the coefficient for the mixed derivative, and C is equals to negative 1. Substitute A, B, C in the formula of the discriminant, so it seems that B squared minus 4AC is equals to 13, a number which is positive, and therefore we conclude that the given PDE is hyperbolic. Second equation, 4 del 2u del x squared plus del 2u del t squared equals to u. Let us determine the type of the equation by firstly shifting u to the left side and compare this equation with the general equation given in equation number 1. Okay, so it seems that A, the coefficient of del 2 del x squared is equals to 4 in this given PDE. Now there is no mixed derivative, therefore B equal to 0 and C is equals to 1. Now this term here is comparable to the term shown here. That means F must be equals to negative 1. Okay, but F is not used in the calculation of the discriminant. So B squared minus 4AC using these values seems to be equals to negative 16, a number which is less than 0, and therefore we conclude that this given PDE is elliptic. Move on to the third question. Del 2u del x squared plus 6 del 2u del x del y plus 9 del 2u del y squared equals to 0. What type of equation is this? Okay, so we can determine the type of the equation based on the constants A, B, and C. Okay, so in this PDE, A is equals to 1, B is equal to 6, and C is equals to 9. Now substitute these constants into the formula for the discriminant B squared minus 4AC, and the answer is equals to 0, and therefore we conclude that this given PDE is a parabolic equation. In this next example, we are going to find the value of an unknown k if the given PDE is classified as A, parabolic, B, elliptic, and C, hyperbolic. Okay, so let us solve the problem. We shall start by firstly shifting del 2u del y squared to the left side to get the following form. And from here we can determine the constants A, B, and C. Okay, so it's very clear that A is equals to k minus 1, B is equals to 3, and C is equals to negative 1. Substitute into the formula of the discriminant B squared minus 4AC, which is 3 squared minus 4 times k minus 1 times negative 1. 3 squared is equals to 9. Now negative 4 times negative 1 gives positive 4 multiplied by this factor k minus 1. Open up the bracket, so we get the result B squared minus 4AC is equals to 4k plus 5. Now in part A, we are asked what is the value of k if the equation is parabolic. Now we know that equation is parabolic if the discriminant is equals to 0. That is 4k plus 5 is equals to 0. So from here we can say that k must be equals to negative 5 over 4. In part B, we are asked the value of the constant k if the given equation is elliptic. Now, the equation is elliptic if the discriminant 4k plus 5 is less than 0. In other words, k can be any number which is less than negative 5 over 4. For example, k is equals to negative 2, because negative 2 is smaller than negative 5 over 4. And in part C, what is the value of the k if the given equation is hyperbolic? The equation is hyperbolic if 4k plus 5 is larger than 0. In other words, k can be any number which is larger than negative 5 over 4. For example, k is equal to 0 because 0 is larger than negative 5 over 4. Alright, so these are the answers for parts A, B, and C. Solution of a PDE. Let us refer to equation number 1 again. So this is the linear PDE, where u is the dependent variable and x and y are the independent variables. So the solution of this linear PDE is a function u of two independent variables x and y. The general solution of the PDE includes all possible solutions, and it typically includes arbitrary functions. A particular solution of a PDE is a solution without arbitrary functions. The particular solution for a given problem can often be found by using the specified initial and boundary conditions. Okay, so recall that an elliptic PDE is an equation that involves partial derivatives with respect to spatial variables only, and therefore the particular solution of an elliptic equation can be determined by using the boundary conditions alone. Whereas for the parabolic equations as well as the hyperbolic equations, these two equations involve derivatives with spatial and time variables, and therefore the particular solution for parabolic and hyperbolic equations can be determined by using both initial and boundary conditions. Let us now start discussing about the method of separation of variables, which is a useful technique for solving linear PDEs. This method proposes a general solution in the form of u of xy, and this general solution is expressed as a product of two functions x and y, okay, where x is a function of x alone and y is a function of y alone. So notice that we write or we use capital letter X and capital letter Y to denote the functions, and we use small letter x and small letter y to denote the variables. So the general solution u of xy is equals to the product of x and y of y, or simply u is equals to x times y. It follows that if we want to evaluate the partial derivative of u with respect to x, we can rewrite it in another form. U is given by x times y, so let us replace this u by x times y. So del u del x becomes del of xy with respect to x. Now x is a function of x alone and y is a function of y alone. When we evaluate this derivative with respect to x, it means that y is considered as a constant. Okay, so we are actually going to differentiate only x with respect to x. Now at this stage here, a single independent variable is involved, therefore it is sufficient to use ordinary derivative in the form of dx. In terms of the prime notation, dx can be replaced by x prime, and therefore del u del x from partial derivative is reduced to ordinary derivative in the form of x prime y. For del u del y, it is the same as del of xy with respect to y. Now here, x is a function of x alone, therefore x is considered as a constant. Since y is a function of y alone and we are differentiating y with respect to y, so del y becomes dy. Because here the derivative involves only one single independent variable, therefore it is sufficient to use ordinary derivative d. Okay, so del u del y becomes x dy, but dy can be rewritten as y prime. So del u del y from partial derivative now becomes ordinary derivative in the form of x y prime. Del 2u del x squared is equals to del x of u, but u is xy. But we know from our previous evaluation, del of xy of del x is equals to x prime y. So again, to replace this by x prime y, okay, so now we are going to evaluate the partial derivative of x prime y with respect to x. Now again, this is a function of x alone, so we write dx prime dx of y. Okay, we change from partial derivative to ordinary derivative because this is a function that involves only a single independent variable x, but the x prime dx can be rewritten as x double prime, and therefore del 2u del x squared is the same as x double prime y. Del 2u del y squared is equals to del y del del y of xy, and here we already got the answer from this part where del del y of xy is equals to xy prime. So replace this as xy prime, so this whole expression is now become del of xy prime del y. But x is a function of x alone, and therefore we are going to differentiate y prime with respect to y. So it becomes x dy prime dy. But dy prime dy can be rewritten as y double prime, and therefore the partial derivative del 2u del y squared now becomes ordinary derivative in the form of xy double prime. The following is the basic procedure for applying the method of separation of variables. Firstly, we will be given the PDE, and we assume that the solution will be in the form of u of xy is equals to x as a function of x multiplied by y as a function of y. Okay, in other words, u is equals to x times y. Then substitute u of xy and its derivatives into the given differential equation. Once this is done, start separating the variables so that the functions depending only on x are on one side and the functions depending only on y are on the other side of the equation. After that, set both sides of the equation equal to a constant to yield two ordinary linear differential equations. So in practice, it is convenient to write the constant as negative lambda. Now we can actually use lambda instead of negative lambda, because these two will also lead to the same solutions. Solve the two resulting ordinary linear differential equations by considering different cases for lambda. That means we should consider the case when lambda equal to 0, when lambda is negative, and when lambda is positive. Okay, so these are the steps in order for us to apply the method of separation of variables to solve a given linear PDE. Now let me illustrate to you how to apply the method of separation of variables to solve a second order linear PDE. Example, use separation of variables to find the product solutions for the partial differential equation given by del 2u del x squared equals to 4 del u del y. Okay, so for this PDE, we know that the solution is in the form of u of xy equals to x multiplied by y, where x is a function of the variable x alone and y is a function of the variable y alone. So u of xy is a product of x and y. So this is considered as the product solution for the PDE. Okay, so this is the given PDE. Now, based on the fact that u is equals to x times y, we have learned from the previous slides how to transform partial derivative into ordinary derivatives. Okay, so we get del u del x equals to x prime y, del u del y equals to xy prime, del 2u del x squared equals to x double prime y, and del 2u del y squared equals to xy double prime. Okay, so for the left side of this equation, del 2u del x squared is replaced by x double prime y, and on the right side, del u del y is replaced by x y prime. Okay, so the equation becomes x double prime y equals to 4 times x y prime. Now for this differential equation, the independent variables are x and y. But for some other problems, the independent variables may not be x and y, but probably x and t. So if that's the case, simply replace every y in these derivatives by t. Okay? So after forming this step, we are going to separate the variables. X double prime divided by 4x equals to y prime divided by y. So the function in x is placed on one side of the equation, and the function in y is placed on the other side of the equation. The constant 4 can remain to be on the right side, or it can be moved to the left side as shown in this expression. Okay. Now x double prime divided by 4x equals to y prime divided by y. Now this is an equality. This is a function expressed in terms of the variable x alone, and this is a function expressed in terms of y alone. So how can they be equal? They can only be equal if they are both a constant, and therefore we shall call the constant as negative lambda. From this, we can obtain two ordinary linear differential equations, which are as follows. The first one is x double prime divided by 4x equals to negative lambda. Simplify to get the following expression, x double prime plus 4 lambda x equals to 0. So let us label this equation as equation number 2. And the other equation is y prime divided by y equals to negative lambda. Simplify this equation to get the following expression, y prime plus lambda y equals to 0. Let us label this equation as equation number 3. So equations 2 and 3 are considered as ordinary linear differential equations, and they will be used in the remaining part of the solutions for this PDE. Lambda as a constant can be a number which is equals to 0, less than 0, or larger than 0. So we're going to consider the first case when lambda is exactly 0. Let us substitute lambda equals to 0 into equation number 2, which is x double prime plus 4 lambda x equals to 0. So if lambda equal to 0, the equation becomes x double prime equals to 0. Now this is just an ordinary linear differential equation. We can solve it by using the technique that we have learned in chapter 4. We start by finding the corresponding auxiliary equation, which is m squared equals to 0. So solving this second degree auxiliary equation, we get two roots, and both of the roots are equals to 0. So this is a case of repeated roots, and the corresponding solutions are x1 equals to e to the power of m1x, but m1 is equal to 0, therefore the first solution x1 is equals to 1, and x2 is equals to x multiplied by the first solution. So x multiplied by 1, therefore x2 is equals to x. And therefore, the general solution for the function x in terms of the variable x is equals to c1x1 plus c2x2. Okay, take note that x is a function of x alone, and therefore the expression for the solution must only be in terms of x. So do not write c1y1 plus c2y2. Instead, it should be c1x1 plus c2x2. Okay, so in other words, x of x is equal to c1 times, now x1 is 1, plus c2 times x2 is x. Okay, so this is the solution for the function x in terms of the variable x. Now let us substitute lambda equal to 0 into equation number 3, which is given by y prime plus lambda y equals to 0. Okay, so this time this term goes to 0. So we are left with this equation y prime equals to 0. Now this is a first order linear differential equation, and therefore the corresponding auxiliary equation is just m1 equals to 0. Okay, there is only one root corresponding to a first order DE, and the corresponding solution will be y1 equals to e to the power of m1y. Substitute my by 0, so y1 is just the number 1. So we write down the solution, y of y is equals to c3y1. Now we use c3 because we have already used up c1 and c2. So the next constant, we label it as a c3. So y of y is c3 times y1, but y1 is 1, so y of y is c3 times 1. Okay, therefore y of y is equals to c3. So this is the solution for the function y. So for case number 1, the product solution will be in the form of u of xy is equals to x times y. X is a function of the variable x alone, and y is a function of the variable y alone. So let us multiply these two results together. So the answer will be u of xy is equals to c1 plus c2x, okay, multiplied by c3. Alright, so this is considered as the product solution for the given PDE in the case of lambda equals to 0. Case number 2, lambda is negative, that is lambda a number less than 0. Let lambda equals to negative alpha squared where alpha is larger than 0. Now why is it necessary to square the alpha and multiply alpha squared by negative 1? If alpha is squared, that means this number is guaranteed to be positive. And when a positive number is multiplied by negative 1, lambda will surely be a negative number as required in case number 2. Substitute lambda equals negative alpha squared into equation number 2, okay, which is this one. Okay, lambda will now be replaced by negative alpha squared, so that the equation now becomes x double prime minus 4 alpha squared x equals to 0. Now this is a second order ordinary linear differential equation, and we can solve it by forming the corresponding auxiliary equation m squared minus 4 alpha squared equals to 0. Now this left side of the equation can be easily factorized in the form of m minus 2 alpha times m plus 2 alpha, and the equation is equals to 0, and we can get the two roots m1 equals to 2 alpha and m2 equals to negative 2 alpha. Let us now write down the corresponding solutions. The first solution is x1 equals to e to the power of m1x, where m1 is 2 alpha, and the second solution x2 is e to the power of m2x, where m2 is negative 2 alpha. And therefore the general solution for the function x is x of x is equals to c1x1 plus c2x2, or x of x is equals to c1 e to the power of 2 alpha x plus c2 e to the power of negative 2 alpha x. Now if we know the definition of hyperbolic cosine and hyperbolic sine, we can say that this equation is actually equivalent to the following expression. X of x is equals to c1 cos 2 alpha x plus c2 sin 2 alpha x. Okay, so to get from this step to this step requires some work. So as of now, just accept the fact that these two equations are equivalent. So you can use either one of these expressions to write down the product solution for the given PDE. Okay, now let us substitute lambda equals negative alpha squared into equation number 3. Okay, which is y prime plus lambda y equals to 0. Replace lambda by negative alpha squared, so the equation becomes y prime minus alpha squared y equals to 0. The auxiliary equation will be in the form of m minus alpha squared equals to 0. Now there will be only one root because the equation is of first order, and the root is m1, which is alpha squared. Therefore, this corresponding solution will be y1 equals e to the power of m1y is equals to e to the alpha squared y. And therefore, the general solution for the function y is c3y1, which is y of y is c3 e to the power of alpha squared y. Okay, y1 is e to the alpha squared y. So notice that x is a function of x alone. Okay, so we write x of x is c1 x1 plus c2 x2. Let me remind again, do not write this as c1 y1 plus c2 y2. And y is a function of y alone. Okay, so y is equal to c3 y1. So everything in this expression is in terms of the variable y. So the product solution for case number 2 is given by u of xy is equals to x multiplied by y. Now x of x, as you got here, is c1 e to the 2 alpha x plus c2 e to the power of negative 2 alpha x multiplied by y of y, which is c3 e to the power of alpha squared y. Now if you want to use the definition of hyperbolic cosine and hyperbolic sine, then the particular product solution for the given PDE is given by u of xy is equals to c1 cos 2 alpha x plus C2 sinh 2 alpha x multiplied by C3e to the power of alpha squared y. Okay, so this is the result for case number 2 where lambda is negative. Case number 3 is when we consider lambda as a positive number, that is lambda larger than 0. Now let lambda equals to alpha squared, where alpha is larger than 0. So by squaring the alpha, we are guaranteeing that this lambda is always a positive number. Substitute lambda equals to alpha squared into equation number 2. Okay, so this is equation number 2. Replace lambda by alpha squared, so the equation becomes x double prime plus 4 alpha squared x equals to 0. The auxiliary equation will be in the form of m squared plus 4 alpha squared equals to 0. Solve this equation. We get m squared equals to negative 4 alpha squared, that is m is equals to plus or minus square root of negative 4 alpha squared. Now here notice that we are getting complex root and its conjugate, where m1 is equals to 2 alpha I and m2 equals to negative 2 alpha I. Now the solutions when the roots are complex conjugates are as follows. x1, the first solution will be cos 2 alpha x, and x2 will be sine 2 alpha x. And therefore, the function x in terms of the variable x alone is c1x1 plus c2x2, which is c1 cos 2 alpha x plus c2 sine 2 alpha x. The next step is to substitute lambda equals alpha squared into equation number 3. Okay, y prime plus lambda y equals to 0. Replace lambda by alpha squared, so we get this equation y prime plus alpha squared y equals to 0. The auxiliary equation is m plus alpha squared equals to 0. This shows that m is equals to negative alpha squared. Alright, now let us write down the solution. y1 is e to the m1y. Now m1 is equals to negative alpha squared, and therefore y1 is e to the power of negative alpha squared y. So the general solution for the function y in terms of the variable y alone is c3y1, which in this case is c3 e to the power of negative alpha squared y. Okay. So finally, we are going to form the product solution for case number 3. U of xy is equals to x multiplied by y. Now x in terms of the variable x alone is given by c1 cos 2 alpha x plus c2 sine 2 alpha x, and y as a function of y alone is given by c3 e to the power of negative alpha squared y. Okay, so this is the product solution for the given PDE for case number 3. Okay, so we have seen the result for the product solutions for the 3 different cases in solving the given PDE. So that's the end of today's lesson. So what have we learned? We focused mainly on second order linear PDE, and we have also learned how to classify the PDEs according to their types. The equations may be parabolic, elliptic, or hyperbolic. And we have also learned how to find product solutions of second order linear PDE by using the method of separation of variables. And to solve, we need to consider 3 different cases when lambda equals to 0, lambda is positive, and lambda is negative. So that's all, and all the best to you, and thank you for your attention.